Okay. So, let's see. Currently, the chapter 17 assignments are due Thursday because I wanted to talk a little more about formulas for power before I have to do. So we will officially be finishing up chapter 17 today. We will try to segue into talking about magnets as soon as possible because despite their ever-presence in our general lives, physicists still don't understand how they work, so it's important to talk about them and figure out what we do know and how we can use them despite the fact that we don't know why they work.
Wait, just quickly, chapter, have you changed the due date on your sign for it?
Oh, I probably haven't yet.
Because like I saw it Tuesday and then I remembered you said Thursday, but then I don't know if you like.
Thank you for reminding me.
One of them was Tuesday and one of them was Thursday. I think the quiz was Thursday.
Changing one, forgetting to change the other does sound like something that would happen to me. So I apologize, everyone. I'm going to do that now before I forget, because I will forget. And I don't want to do that to you guys. Let's see. Apparently, right?
On the homework, when on 2 of the questions when I get an error, it tells me to like think about something, but I don't understand what it's telling me to think about.
That's not a helpful comment on the sign. I'm sorry.
Because it's the one with like the currents for the two like I got the like when you do like the resistance stuff and you're trying to find the total resistance. Like I got that right, but when you do like the current, I think it's 5.
Okay, number 5.
I think.
I'm changing the schedule and I need to, and then I'll look at the questions, all right?
Let me look at it so I can make sure I get it right. Because like I said, I got every part of the question right. I might be 7. It might be 7 and 8 or 2. And I just haven't got 5 maybe.
Okay, the assignments are now rescheduled for Thursday, which coincidentally is April 1st, but this due date is not a joke.
Wait, it's April 1st, Thursday?
Yep.
Is there 31 days?
March has 30 days, 31 days, wow. 30 days has September, April, June, and November, all the rest are 31 except shall February.
Why do they do that? It should just all be 30.
Yes. Someone calculated the exact, number of times that the Earth spins about its own axis as it rotates around the sun. And that number of days is 365.25. And someone decided that was the best way to chop it up, probably because
Or like the length of the day and the night is the month, right?
I don't think so. Calendar used to have 10 days, and then they added January and February.
Wait, what did you say?
10 more.
Sorry.
He said
Calendar used to have 10 months, excuse me. The calendar used in most of Europe used to have 10 months as of like the Roman era. But they added January and February to make things more precise. And January was able to have a consistent number of days, but February wasn't, I guess. It's a big mess, and it's tied back to the Romans, who were all insane, so that doesn't help. Okay.
it's 7. It's 7A, the second question. What is the current in each resistor?
7A. I apologize for the unhelpful comment that my son made.
And it's the same thing on 8E, but it was the same kind of question. I still get what's asking. Because like for current and like it's a series, right? So isn't the current all the same?
Yes, it should be. So, number 7, we have 3 resistors of some size connected in series to some battery of some size. Bar, okay. This is a series circuit, so equivalent resistance should be just the sum of the three, and based on the numbers on the screen, 6.3 plus 6.3 plus 6.3 should be 18.9 ohms. What then is the current in each resistor? This is a series circuit, and the rule for series circuit is the current is the same for every single resistor, and everything gets its own different voltage drop. So, for 7B, for 7B, we want to do Ohm's law, V equals IR, the total circuit voltage and the total circuit resistance will tell you the total circuit current, and in a series circuit, the total circuit current is the current that every piece gets. Because the current coming out of the battery has to go through every single one of them, there's no other choice. So, for 7.A.2, the second part's not really labeled, V equals IR, using the answer you found in the first part as your R, the battery voltage for V. Then it says 3 other resistors are all connected in parallel across a different battery. So this is a separate circuit. This is a completely separate circuit, and it could have worded that better. So same numbers in a different orientation, and the rule for how to find the resistance here is a little bit different. This is the formula that is the inverse sum of the inverses, which just put it on board for you guys real quick. It is important to note that once you add up the inverses, you have to take the inverse of that sum, because it's 1 over total R equals blah, blah, blah. So if this gives you like 0.03, you have to do 1 over 0.03 to get the actual number. And in general, wired in parallel, total resistance always goes down, because by virtue of it being parallel and having multiple branches, you've made it easier. So when you're working it, if you get a smaller number here than this number, good. That is the goal. Then what is the current in each resistor in this circuit? So whereas in series, every resistor gets the same amount of current because that current travels through all of them one after the other. In this situation, every resistor will get, they will all get the same amount of current in this case because every branch has the same resistance, but whatever current exits the battery is going to get here and split 3 ways. So if you were to do V equals IR with the total circuit voltage and the total circuit resistance, you will get a current, total current, and that would be what comes out of the battery, but that current will split before it hits any of these resistors. So whatever you find, whatever this I is not going to be the ultimate answer. Now, there's 2 ways to get to the correct answer here. One of them only works because all of the R's are the same. In this specific situation, since all of these resistances are the same, the current would go down each one of them evenly. It's just as difficult down every single branch, so the current should split evenly into thirds. So whatever this number is, divided by 3. That doesn't always happen. They aren't always the same resistance. This is one of the few times this occurs. The more technical advice that would give you the answer every circuit, no matter what the resistance is, what you want to do is V total equals current through resistor 1 times resistance 1.
Wait, so V stays the same?
Yes. So the rule in a parallel circuit, so over there we've got current same for every resistor and voltage is different for every resistor. Here it's the complete reverse. The current will split, but the voltage drop is the same for everything. The reason for that is, if this is a, what's the number it gave us? 23 volt battery, that's not a standard size, but sure, we'll roll with it. This is a 23 volt battery. That tells us that the positive end of the battery is 23 volts higher than the negative end of the battery. And the current is going to want to go through the circuit from positive to negative. And voltage drops across resistors. Going through a wire doesn't really drop much. It's when you hit a resistor that the voltage kind of gets used up and it drops across the other side. And in a parallel circuit like this, we've really only got two zones here. We've got an entire region before the resistors, where the potential is 23, and an entire area after the resistors, where after which point the voltage will have dropped and now the potential is 0. So in parallel, everything has the same voltage drop, which in this case is the same as the battery. So I wrote down total V to remind you that it should be the same voltage as the battery, but that battery voltage is also going to be the individual voltage drop for each resistor. And you said number 8 was similar?
Yeah, I think I got it though, because it was the same issue. I was just dividing them on numbers. Like I had the right concept, I was just dividing them apart.
Oh yeah.
Because I got a bunch of stuff, and I'm still the last one.
8 is a combo, oh, okay. Part A of 8 is looking at this combo circuit. What is the equivalent resistance? Number 8 steps you through finding the equivalent resistance of this entire circuit. Everyone will have a couple of different numbers there. From the resistance, what is the current from the battery? So here, total voltage, total resistance would be the total current.
Well, yeah, that's where I got stuck, but then I realized it was in their series circuit because it was the V over R, and then I had it backwards.
Yeah, it doesn't matter what kind of circuit. Total voltage will equal total current times total resistance. What happens to the voltage drops and the currents after that point will depend. But for the whole circuit, total V equals total I times total R. What is the current in the battery? So this is the total current. This is the total current that I just mentioned. Then what is the voltage drop of SR2? Okay, so that's where the F onwards is where this one might start to get tricky. This is where you have to start looking at how it will divide up within the combo part. And this is due Thursday. So I'd like you guys to be working on it, try it, come with the questions that you encounter on Thursday. I want to transition now into talking about electrical power, so we can finish off the 17 notes and have everything you need to be able to finish the whole assignment. Yes.
I just want to ask really quickly, I forgot what days you said we have lab and what we don't.
Okay, good question. That does segue neatly into an announcement or two. So, now today is March 30th, so this week will begin in March and end in April. Lab this week will still meet. There is a wellness day that the school has officially declared no classes on. That doesn't affect our lab, but we won't have lecture that day at the very least. So no class this day, but yes, lab this week. To go ahead and talk a little bit about that lab, it's going to serve as an introduction to some magnetic principles, because I want to go ahead and start showing you those, because as weird as some electrical principles are, magnets are even weirder.
So I want to go ahead and begin showing you those before we start doing much math about them. Because this is an introduction to magnets, and because, like with electric fields, you can't really see magnetic fields, there will be some simulator elements to it if my plans all go, if my plans go as planned. There will be some simulator parts, but also some physical parts where you'll actually get to manipulate a magnet and show that it has an effect on electrical systems. If that goes to plan, then we do have lab this week. You come to lab, we will work on the physical part together, and then you could work on the simulator part with me in the room or elsewhere. You can just turn it into me by the end of the week. Next week, also lab. There is no, well, wait. We have Monday off for Easter. But after that point, normal week for this particular class. So yes lab next week, yes lab this week, yes lab next week. The week after that, no lab, because there's a wellness day on Tuesday the 13th. I'm very happy about that. Man, do we need them, students and teachers. So, Cliff's notes, lab yes, lab no, to be announced for the rest of the semester, because as we get to the end, we'll focus more on exams.
Is that 21 the honors day?
Yes.
They said Wednesday, right?
Yes, they did.
Okay.
Yes, 21 is honors day because my other lecture, I had to dance around the test around that. Not this class, my other section. Schedule questions? Okay. Please work on the homework. Please come with questions on Thursday. Admittedly, yes, this part might be the trickiest part of the assignment. Do go ahead and start it so that I know exactly what is more difficult for you guys. My goal for right now is finish up electrical power so that we can close the book on the 17 notes. Speaking, before we begin with that, any other questions from anybody? Okay. Let us, so, now, these formulas might not be brand new. I've shown you power formulas in lab, and you have definitely talked about and used power before. We've talked about power before in this class together, if nothing else, because we talked about thermal power, rate of thermal conduction. Power in general is still defined as the use of energy over time. You are utilizing power, you are doing work, using energy to accomplish some task in some amount of time. And this is true for circuits as well. Whenever you plug something physically into a circuit, it's going to draw energy from the electrical current and use that energy over time to accomplish the task of whatever the machine was built to do. In the circuits that we've been dealing with, the resistors, like the physical little peanuts on sticks resistors in lab, aren't really designed to do much. Their purpose is just to be a resistance and eat up energy out of the current so that the current is what you want it to be when it hits something else. But given that a resistor is anything you can plug into a circuit, we could put 3 light bulbs in here, and the light bulbs, what act as a resistor, they take energy away from the current and then use that energy to be on. Now, it's not actually on the board, so as a quick refresher, power is still defined as work over time. That is still true. The unit for power is still watts. And I would say that in general, is it a fair assumption that in English vernacular, the word watts is used mostly in conjunction with electricity. So we're like after a year and a half of physics, it's finally now being tied into electricity. Like the word itself is just energy over time, but we tend to use it mostly with electricity because American power companies bill us in terms of kilowatt hours of energy used. So unless you're doing the physics and talking about watts in other contexts, it's the only case line you can hear the word. So still watts, still work per unit time. We've W's for a lot of things here, unfortunately. Now, in a circuit, power used up by any given part of the circuit, you can look at power used up by the whole circuit, you can look at power used by a specific piece of the circuit. That power can be found a number of different ways. The primary main formula is power is equal to, power used up by something in a circuit is equal to the current running through that particular piece times the voltage drop across that particular piece. So let's say we're looking at this circuit here. We find the total current passing through every element. We just know that the current will be the same for all of them. They're all going to have a different voltage drop, which we can calculate by using total current with each individual resistance to find each individual voltage drop. The individual current times voltage drop for just this particular piece would tell us the power used up by this resistor, which would be the energy it is burning every second. And that's energy that is now no longer in the battery because the resistor is just turning it into thermal energy and removing it from the current. You could also, if you were to use the current passing through the whole circuit and the circuit's circuit's total voltage, so total current, total voltage, if you plug those in, you could find the power used by the entire circuit at once, which would be a better representation of how much energy is being drained from the battery simultaneously. In general, though, the power used by each individual element of a circuit should add up to the power used by the whole circuit at once. Yes?
In this case, will delta V always be voltage drop?
Yes, we call it drop because all of the formulas that involve voltage on a technical textbook level are always delta V because it's the change in potential that actually drives the current forwards. If the potential was the same in two places, then the current wouldn't flow. It's like trying to make water flow across level ground. There needs to be a difference in potential for a flow to happen. And so if there's a drop across a resistor, then the voltage will actually force the current through that resistor. So all voltages are technically voltage drops. You could calculate just the total potential in one area, but that means nothing unless there's an area nearby with a different amount of potential.
So if there, would that be like if there was two batteries? And like they had different voltages?
Well, it's like, isn't it the ends of one battery that have the different voltages?
Correct. And how you wire them will affect what happens there. If you wire them in series, you can build on that total voltage. If you wire them working against one another, it will probably cancel out, nothing will happen. So this is sort of the original version of the formula, but what is physics but taking formulas and mashing them together to try to find something we weren't supposed to. And people combined Ohm's law with P equals IV, and that gave us these two additional variations. They all equal the same thing, it's just a question of how Ohm's law was used to take one thing out and put a different thing in. So they're all equivalent. Power equals current through something times the voltage drop across it. It can also equal voltage drop across an object squared divided by its own resistance. Alternatively, it can equal current through it squared times its own resistance. All the same thing, they'll all tell you the same information. Which one you use can just be a matter of preference, alternatively, what you happen to know about the system. And so those are the factors that just determine exactly how much energy a particular appliance will heat up. And every appliance takes a different amount depending on how much current it needs and its own internal resistance typically are the main factors. So, sample question. This is the same resistor that we calculated, the tungsten resistor that was built, and we checked what its resistance would be at 2 different temperatures. So the numbers are unchanged, so we can dig up those resistances calculated. Does anyone happen to have those quickly at hand?
18.2.
Okay, 18.2.
And then the current was 6.59.
Oh, yeah. Yeah, can you tell me that current one more time?
6.59.
All right. So we build this resistor, we plug it into its power source, and at this temperature, it has this resistance, and there's this much current running through it. We also found how that would change at 3,000 Kelvin. Why does my K look like that? That's a little more normal. And when you increased its temperature, its resistance rose to 256.
I have 239.
Thank you. Yes, that's it. 239.9 ohms. And since its resistance went up and the voltage stayed the same, what happened to the current passing through?
It dropped
It dropped to
0.5.
Q. So, for this one object, we have 2 resistances and the 2 currents passing through it at those 2 resistances. We can use this information to determine how much power the resistor was using at each of these moments in time. So let's use these numbers to determine the power consumption. Our starting formula was P equals IV, officially delta V, I'll try to be consistent. With just what's on the board, with just what was written down, does this by itself help us? No. So we can instead use one of the alternate versions. Just as a sample, if we know for certain resistance and current, then we can look at the specific version that has I and R in it. And I believe that was I squared times R. So that version would save us from having to dig up or solve for another number. So I'm in favor of using that one. So power at 20 degrees Celsius is going to be the current at that temperature squared times the resistance at that temperature. And the same at 3,000 Kelvin. before doing the math, just baseline guess, no wrong answers, which do you think is going to be the bigger number?
The is 7.7 is like 49,
Correct.
and then times 18 versus something times 239, but then sometimes square is weird.
Correct. The limiting factor here is we're squaring a number between 0 and 1. And that's going to make this decimal even teeny tinier. So, spoilers in a second, the top one will end up being the larger number because this is at least a larger integer being squared times a decent sized number. This is just going to get too small to really matter much. Well, it matters, okay.
Well, it's like a fraction, so it's like making it smaller
Right.
versus, yeah.
Square a fraction, it becomes an even smaller fraction. That is a good way to put it. And please tell me if your answers disagree. I have 791 watts versus 60 watts.
Does it matter if we got different places or not? Because I had 790.3.
That's fine.
Yeah.
59.9.
That should be, that is, if I was a human being grading that number, that is fine. And I told Lev assign to be okay with 5% difference so that if the computer yells at you for that, please let me know.
Just really quickly, when it says 10% difference, does that mean that you're off a place value?
No, when it's multiple of 10, that's when you're off place value. 10% means like your answer's close, but it's not close enough.
Yeah, so 10% of, like, if the correct answer is 60, within 10% of 60 means it should be okay with any number between 54 and 66.
Oh, okay, yes. 10%, yes.
Also, I have a question.
Yes.
So when you're finding, technically it's a step up, but on WebAssign, I really struggle with one because I figured it out by the end. But, so if they're giving it to you in Celsius and they want you to find the temperature in Celsius, you keep that number in Celsius, right? Like you had to find the ending.
Oh, for the resistances?
Yeah, like it gave you both resistances and like everything else. You had to find like the end temperature.
Right.
And like I first did it in Kelvin, but when I did it in Kelvin, I got the wrong answer.
So the formula that has the T's in it, back up, circle slides. The formulas with the T's in it is effectively a delta T. It's 1/10 minus another. So like this delta T will be the same number Celsius or Kelvin as long as the both numbers you plug in are the same unit. So if it gives you Celsius and you keep it in Celsius, the other number should come out as Celsius.
I got it right like at the end. I just had to do something because I didn't think it mattered, but it did. And it really changed it a lot. Because once you derive that formula to find temperature, like you have to add, do a lot of dividing and adding to get temperature right now. Not a lot, but a lot more than I would like.
Yeah, I think I had trouble with that same. I did the same thing, and I
Okay. We look at that with you guys later. I want to.
No, that's fine. I was just saying because I didn't know what time it is. So I was curious. But you're good.
In general, whatever you put in should be the same thing you get out. So put in Celsius, you'll get Celsius out. Now, given that I understand that not all of my students are ever going to be physicists or do physics with math ever again. So with that in mind, I want to talk briefly about how the thing we just did is at least tangentially useful to how your electric bill is calculated. Because that is something you'll be dealing with until the end of the universe.
Or at least, yes.
So, in the United States, and probably other similar places, if you were to, say, look at your electricity bill, it will tell you a dollar amount per, so let's just say, let's get in this here. All right, so on board right now, we're told that for this sample question, the cost of electricity is 10 cents per kilowatt hour.
Wait, okay, so watt is per second, joules per second. So if you're multiplying by hour, what happens to your unit of time within the watt?
That is an excellent question, and it's a question that the American Power Grid doesn't really care too much about. The unit of kilowatt hour is exactly what it says on the tin. This is 1 kilowatt times 1 hour. And this is not a standard metric unit. This is American nonsense, frankly. Like, metrically, empirically speaking, this gives people fits. I look at it and I get mad sometimes. But technically speaking, what they've done here is power is defined as work over time. If you were to rearrange this a little bit, you could get power times time equals work. And this is technically a unit of power, kilowatts, times a unit of time. So it's not a good unit for energy, but it's a unit for energy. And it's one that the American Power Grid uses because it's nice and big, and it saves us from having to, like, since the unit is large, that makes all of the actual numbers smaller. So, as a quick sample, let's say, I've had to look up a few of these figures before, let's say that your television has a wattage of 100 watts. Every single appliance you buy has a wattage written on it that tells you the power needs to stay on. That's the amount of energy it needs every single second to remain functional. So 100 watts, it needs 100 joules every second to stay activated. And what's a good figure for how long your TV's on at night? 5 hours on a good weekend? Actually, no, 5 hours on a weeknight is accurate for me. So, let's say that our 100 watt TV is turned on for 5 hours. In order to find the kilowatt hours the TV is turned on by, you just literally multiply kilowattage by the hours it's turned on. So 100 watts in kilowatts would be 0.1 times those 5 hours. And that means that every night, this TV is using 0.5 kilowatt hours of energy. Again, this is not a very good unit of energy, but this is energy spent. Since it's power times time, this is the total amount of energy used. So it's not equivalent to joules, but it's analogous to joules.
But it's like an unsimplified unit. isn't it?
Correct.
Right?
Yes.
Because like, if you do factor in the seconds, hour over second should not give you, I don't know what it gives
is an
you.
unsimplified unit, and as far as the power grid and the legislators are concerned, that's all they care about. So this is more a lesson in dealing with the situation more so than the sense that it makes. So, if this TV was on for 5 hours, it would use this much energy, and 1 kilowatt hour is 10 cents. So, that would charge you 5 cents per night. That's all it costs to keep the TV on, 5 cents per night. know your parents always told you turn the lights off and burn the electricity. Light bulbs have a lower wattage than this. Light bulbs are not the biggest part of your energy bill by a wide margin.
Is it your air conditioning?
Your air conditioning and your refrigerator, because they're always on. And because they're heat pumps, which take a lot of energy inherently. The biggest parts of your electricity bill are always your refrigerator and then your either heater or AC, depending on what time of year it is. After that, probably your oven, then maybe your microwave, then maybe a big gaming PC. Your Wi-Fi router is also probably always on. That's a decent sync. So, for the problem up on the board, Dr. Rodekor has been doing a lot of projects about energy efficiency and home costs over the years. I did my basically undergrad thesis with him about the energy use of refrigerators, so I'm very used to the types of problems that have been used in this department in the past. The problem tells us that a CFL bulb, which are the newfangled swirly ones, has a required wattage of 13, which is good, and each bulb can stay on for this long. Meanwhile, the old-fashioned ones with the tungsten filament inside of it, that you can see when it goes dead because it breaks and then rattles, those typically have a wattage of about 60, and they will stay on for about 750 hours before breaking. So, per bulb, let's estimate for the entire lifetime of the light bulb how much having it turned on will cost. Not factoring in even yet the cost of the bulb or the cost to replace them. Let's just look at how much energy it costs to keep them on for their entire lifetime. For the CFL, we've got a wattage of 13. That's going to translate to 0.013 kilowatts times approximately 6,000 hours. And then for the old bulb, I'm just going to call it old for space's sake, 60 watts is going to be 0.06 times, it's only on for 750 hours. So, that gives me 78 kilowatt hours for the new bulb and 45 kilowatt hours for the old bulb. And if electricity is 10 cents per kilowatt hour, that means for the entire lifetime of this bulb, that should cost you $7.80. And for the other bulb, that should cost you $4.50. So, which bulb's better?
The first one,
Why is it the first one?
Because it lasts longer.
The one bulb will last you a lot longer.
But also, like, what's the?
Yes, it does say.
But it's still gonna be more expensive for the bottom one, because that's just one light bulb. And it's only gonna last 750 hours. So if you have two light bulbs, in terms of your 450 plus 450, you're still only at 1,500 hours. compared to the 6,000 hours of the first one.
Correct. So, 6,000 divided by 758. So, for one of these, 8 of these would die and need to be replaced. This wouldn't change. Oh no, actually, this would change. This would be the same for the one bulb. So for the same amount of time, you need 8 more of this.
And then you want to know the more expensive too.
It'd be 36 to 90.
So for this runtime, it would cost this much to use the other type of bulb. So even ignoring per year, this is just per lifetime of one light bulb. And so,
For 1 year, we can multiply it by 12.
Problem doesn't really say how many hours per year each light is on. So
Wait, then how do you answer the question?
as it's written, I'm not really sure. This is the part that I would show you. And I have yet to revise my slides.
Okay, I was wondering if like we didn't answer it wrong, because like I was like, wait, we talked about 1 year, so like,
Now, please go ahead and be packing up. I just want to go ahead, I just wanted to say, as a general home energy cost calculating tip, to find like the total for your entire dwelling, you would want to look at the kilowatt hours used on every single appliance separately. So if this is the amount spent by your TV, your refrigerator, which would have a higher wattage, is on for a longer amount of time. So you would want to multiply that wattage by that time, and then look at the wattage times time for every other machine. And once you have all those separate kilowatt hours, you add them together, and then you use this conversion, if you want the total. And with that, that is all the important things from chapter 17. Talked about these certain times. So the homework, and I've just changed it, please do check though. And the homework and quiz are now due on the Thursday. Well, I was about to say the 30th, on the Thursday. So work on those. We'll have time to look at any questions on Thursday. Send me any questions you have over email as well, and have a good day.
So what are the correct steps? So we're gonna also change that to what first? Right to your power. Or then the is it general resistance and voltage?
Okay. Okay, me looking at this, I think the ohms and the volts might be a trap.
Oh, okay.
Excuse me, sorry. No, wait, it's not a trap. It's not a trap, I apologize.
There's,
So the ohms and the volts, you can calculate to find the power,
Right.
like the wattage of the
Yes.
device. The water and temperature change part is flashing back to heat and thermo. You want to find the energy required to warm up that water.
okay.
So
Is that what it
MC
is?
delta T.
Okay.
That'll tell us the total energy required.
Okay.
That, well, kilowatt hours is energy. So once you have that amount of joules, you could just convert it to kilowatt hours and then convert it to dollars.
And so you just multiply this number kilowatt hours by that?
Well, MC delta T tells you joules.
Right, and you convert that to kilowatt hours? Or kilowatt?
There is a way to do it, and you just don't know the conversion off the top of your head.
I haven't said, I got most of it done this weekend.
Okay.
That one I got really stuck on, and then, like I said, number 8,
So 1 kilowatt hour is equal to 3.6 times 10 to the 6th joules, which is a lot. Yep. So whatever amount of joules you find with MC delta T, you divide by this, that'll tell you kilowatt hours.
And then you can multiply that with hours.
Yes. And that's in dollars, not cents. So yes, you said multiply by that.
Okay.
That is how I would do it.
Okay. So technically, you don't really have to use the ohms and the watt voltage.
Technically, no, because it doesn't exact, I mean, okay, you could figure out the device power, compare that to the joules, use that to find the time that it's on, and then multiply that time by the wattage and find it that way. So I can see 2 ways to do it.
But the other way seems a lot easier. So it's about,
Potentially,
like,
yes.
finding out and then
You're swapping out algebra for a second conversion. So 6 to 1, half dozen the other. Have a good day.
Thank you.